the topic today is, was there really a Victorian internet, which I'm going to tell you everything I know that I've learned in those 25 years about the last 170 years, but compress it down a little bit. So let me fire up my screen here.
I should just say that the Victorian internet was a name invented by Tom Standage, who is
I'll mention him. Yeah, he's
good,
and
he actually spotted my Facebook publicity for this event, but I don't think he or Kirsten, his wife, both of whom live in Greenwich, are on tonight. At least I haven't seen their names. So
I've never met him, but I really liked his book when it came out. It's quite a while ago now.
It was 1998. Yes.
So 24 years ago.
Yeah, exactly. And Kirsten is a local GP. So and we know Tom's mother very well. So it's we have connections with the Standage family.
Yeah, I'll give him my regards. Tell him I still refer to his book occasionally. So
okay. I will, when this is on YouTube, I will pass him. Oh, right. I will pass him the link. Okay. Yeah. I'm going to mute myself now and carry on, Bill.
Okay. So the talk is, was there really a Victorian internet? And the subheading it is, and how did we get from there to Zoom? So to have an internet, which is just shorthand for an interconnection of networks, you first need a group of individual networks that you want to join together. In the mid-1800s, these were the landline telegraph systems of Great Britain, Europe, North America, and eventually many other places. So in 1998, a few years after the World Wide Web introduced today's internet to a much wider audience, Tom Standage wrote a book called The Victorian Internet, in which he drew some parallels between the 19th century telegraph and cable network and today's internet. The book's subtitle is The Remarkable Story of the Telegraph and the 19th Century's Online Pioneers. I recommend it. But was there really a Victorian internet? Certainly not as we know it, with instantaneous low-cost communications available to ordinary people almost everywhere in the world. But by the end of Queen Victoria's reign in 1901, there was indeed a worldwide network of communications cables joining together the landline telegraph systems of many countries. And since then, despite competition first from terrestrial radio, more recently from satellites, wires and cables are the past, present, and future of global communications. And in this talk, I'm going to give a brief history of how it all started and how we got from that Victorian internet to today's internet. And the key connection has always been the link across the Atlantic Ocean, which was first made in 1858. I'm going to describe this in some detail, as it was the beginning of the great expansion of the undersea cable network, which at that time was only 7 years old. I flew over to London last November, where I met Stuart in the gap in COVID. And on the flight, I was watching the moving map display. And I was reflecting, some things have not changed much since then. The fastest route then as now was the Great Circle route. Up the coast from New York, past Boston and Portland, Maine, onto Nova Scotia and Newfoundland, right pretty well over where the cables landed in Newfoundland. And then from there, the long 2,000-mile trek over the open sea until making landfall at Ireland and landing in London. And you can see the route there. And one amazing thing that I found in the cable research is the Irish fishermen used to sail out for the season from the west coast of Ireland up to that portion of Newfoundland and fish for the season and sail back again. Absolutely amazing. But it shows you why the first cables took that route and why even today they still do. So my flight in November took me just 6 hours, but in the 1850s, it would have been at least 3 weeks on a ship. And of course, I made the travel arrangements via websites and email. In the 1850s, you had to do it by exchanging letters over that 6-week round-trip communications network. So how do we get from 6 weeks to just milliseconds for transatlantic communications, and from writing letters to email, Twitter, Facebook, Zoom, and everything else the internet provides? I'm going to condense 170 years of communications history into this talk. So inevitably, I'm going to have to leave a lot out. But I hope to give you at least an idea of the path from Morse code messages of a few words a minute over a copper wire to about 4,000 million words a second over a single optical fiber. And Stuart will probably tell us later that it's now 10 times that since I wrote that sentence. But although landline telegraphy was first introduced in England and America in the 1830s, widespread availability to the public didn't come until the late 1840s. By then, telegraphy was well established in Britain and Europe and in many parts of the USA. The next step was to connect countries separated by the ocean, but this posed a whole new set of challenges. which a completely unrelated series of events came together to solve at that time. Copper wire to conduct the signals was readily available. It was used for bell wire, but these weren't electric bells, but the ones that work by pulling a handle in any part of the house and having the bell ring in the servants' quarters. So it was a mechanical connection of communication. And copper was the ideal material for that application, as it didn't break under repeated strain. But of course, for that use, no thought was given to its electrical properties, and it was highly variable quality. But this could be improved once the need was known. Underwater transmission of signals requires an insulator for the wire, and gutta percha, the rubber-like sap of a tree found only in the British Empire and introduced to Britain a few years earlier, was the perfect material. And it actually started out as a decorative and utilitarian material. Because it's thermoplastic, you could mold it and then it would set up solid again when it cooled down. So you can mold it into a variety of shapes. And this slide is from an exhibition Telcom put on in 1950 to celebrate the 100th anniversary of the very first cable. And you can see all the kinds of things that were made from gutta percha. But of course, it was soon worked out that you could mold it or extrude it around a copper wire. So the last thing that was needed, now you had a wire and the insulation, was to armor the cable with a wire jacket to give it strength during laying and protection against abrasion on the seabed. Cable armoring could be made using the same machinery as the recently introduced iron wire ropes, which were developed to work the hoisting engines in Germany's deep mines. And 19th century industrial espionage quickly transferred this technology to Britain. As I think somebody who knew R.S. Newall was in Germany, he was an engineer, a mining engineer, and he got a tour of a mine and said, oh, how'd you get the cages down so deep? And they very kindly showed him. And when he came back, he gave Newall a note and said, you ought to do this. And so Newall came up, I think, with the first armoring machine, or really stranding machine. He'd been making hemp rope up in Gateshead. And he saw an opportunity to make wire rope. So, and of course, hemp rope you make with a core that you strand your outer around. And here, the core of the cable, as it's still called today, was the copper plus the gutta percha, and you stranded wire around it. So all of this came together at the end of the 1840s. And in 1850, the first undersea line was laid between England and France. And Stuart tells me I can't call this a cable because it wasn't armored. It was just an insulated wire, a copper wire with gutta percha insulation, no armoring. And it was so light that they needed lead weights to take it to the seabed. And that was made and laid by a converted tug. And interestingly, for the time, it was coiled on a drum. And of course, today, and in fact, for over 100 and some years, probably soon after that, the cable was coiled horizontally because it was easier to work that way. Although Stuart and I have also written about Pluto, and they had the Conan drum, and the Pluto undersea pipeline was also coiled the same way, but it was towed behind the ship. So that was kind of harking back almost 100 years. But for Goliath, it was only a 20-odd mile length of unarmored wire, so not very heavy. And this did work long enough to carry a few messages. And the thing is, the Brett brothers who laid it had got a franchise from the French government, but they had to get messages to their connection by a deadline. So they're on kind of a bit tight on this. So they made and laid it in a rush. So it did work long enough to carry a few messages and secure the franchise. But because it wasn't armored and there was wave action off the French coast, the wire abraded and broke almost, I think, within a couple of days. But they got the messages through. But being light, some of it floated away, and at least one length it was hooked by a French fisherman and taken back to shore. And even though he wasn't to blame for the break, it remains a fact that fishing boats are a hazard now to fiber optic cables. A boat hooks a cable with its anchor or trawl, and communication in the area are disrupted. Not to mention undersea volcanoes, of course, which I don't think there's been any other breakages caused by volcanoes. I have by earthquakes, certainly. But just give you an idea of what this wire looked like. This is probably also the first souvenir of an undersea cable. And somebody hauled up a length of it in 1854 and mounted it on a card and sold it. I was lucky enough to find this some years ago. And that's only 11 millimeters diameter, so less than half an inch. And you can just see the copper wire at the left-hand end, and then the coating of gutta percha around it. but it was enough to work. So the Brett brothers secured their franchise, and the next year, it's just amazing what they did in a year after that, because here is the 1851 cable, which looks very much like the cables that have been laid ever since until the end of the copper era. You've got 4 copper wires in the center of this one, gutta percha insulation, and then probably iron wire armoring around it to a diameter of just over 3 centimeters. And the cutaway shows the construction with the, it still has that central core there that wrap the whole thing around, then the 4 insulated wires, and then hemp rope or twine, and then a wrapping of hemp twine, and then the outer armoring. And this was a very successful cable. So by the mid-1850s, there's quite a network of short cables in and around Europe. And the next logical step was to cross the Atlantic. And of course, this was driven mainly by the demands of international trade and commerce, although the government was interested in communicating with its people, embassies, armies around the world. So, but even before landline telegraph systems were in common use, the possibility of an Atlantic telegraph cable had been in the air. In 1843, Samuel Morse, in a somewhat unwarranted yet eventually accurate fit of optimism, wrote, "A telegraphic communication on the electromagnetic plan may with certainty be established across the Atlantic Ocean. Startling as this may now seem, I'm confident the time will come when this project will be realized." So this was 1843, and of course it took 23 years before it was realized. And around the same time in Britain, the Brett brothers, I don't think had even thought about making a connection with England and France, but in 1845, they registered the General Ocean Telegraph Company with the ambition of laying an Atlantic cable. And that same year, they obtained a patent for a telegraph printing instrument, which mentioned its possible use on an oceanic line. So the mid-40s, things were in the air, definitely. Excuse me a second. And then, excuse me, in 1849, American naval vessels began systematic deep sea soundings in the Atlantic. Based on their findings, the hydrographer Matthew Fontaine Maury, superintendent of the Naval Observatory, suggested that there was an undersea plateau between Newfoundland and Ireland, which would be the ideal route for laying a telegraph cable. And as it turned out, it wasn't really a plateau, but it was reasonably free from deep and steep crevices and mountains. And the seabed was covered in foraminiferous shells, the tiny marine creatures. And it was basically a soft, sandy bed. So in 1854, a New York businessman, Cyrus Field, proposed to lay a 2,000-mile Atlantic cable and started raising capital. Little did he know that millions of dollars and pounds would eventually be sunk into the project. Cyrus Field was a wealthy paper merchant who had retired with a fortune by the time he was 33. Unfortunately, he knew nothing of technology, or he would no doubt have pursued other interests in his retirement. The quality of the materials used to make the first cables was inconsistent, their theory of operation was unwritten, and the instruments used were primitive. The short cables which had been laid up to them worked more by chance than design, and there were many failures. But Field knew nothing of this. Having become bored in his early retirement, in January of 1854, he met Frederick Gisborne, a British engineer who a few years earlier had been appointed superintendent of telegraph lines in Nova Scotia. In 1851, Gisborne expanded his territory to Newfoundland, where he persuaded the Newfoundland government to fund a telegraph line across the inhospitable interior of that rather large island. His idea was to take messages off ships arriving at Newfoundland from Europe. They'd be thrown over shore in a barrel, basically overboard in a barrel and picked up and taken to shore. And then he would transmit those messages across Newfoundland by landline, then onto Nova Scotia by a short undersea cable, across the Canadian mainland, then onto New York via the existing telegraph right-of-way, which had landline telegraph running down it. This would give a commercial advantage of almost a week's time in sending messages from Europe to New York, and would hopefully be a profitable venture. But sadly, Gisborne had underestimated the difficulties of his project and ran out of cash. So of course he came to New York looking for investors. And in New York, he met Cyrus Field's brother, Matthew Field, who was a civil engineer. Matthew introduced Gisborne to Cyrus, and the story goes that Cyrus looked at the big globe in his study, which we see in the slide there, and that globe incidentally is now in the Smithsonian, having been donated with a bunch of other stuff when Cyrus died in 1892. So he looked at the globe and wondered why the connection shouldn't just continue from Newfoundland and onto Ireland by means of a submarine cable. This would greatly increase the time advantage of Gisborne's scheme, allowing messages to flow between New York and the commercial centers of Britain almost instantaneously. Fired with enthusiasm, Field wrote to Samuel Morse and Matthew Fontaine Maury with some technical questions. And after receiving their positive response, he started tapping his wealthy New York friends for funds. And you may wonder why he knew all these people. One of his brothers became a Supreme Court justice. One was a very well-regarded minister. His brother Matthew was an engineer. And he lived in Gramercy Park in New York, which today is even posher than it was then possible. Built his own mansion with one for his brother next door, sadly demolished. And he really knew pretty well everybody. And so he tapped into his friends. And later, this group was called the Cable Cabinet. And this is kind of an allegorical portrait. It's large, it's the size of a small wall, and it's in the New York State Museum now. And it shows Cyrus Field in an academic robe, although he had no academic qualifications. And he's looking at the globe, and he has Samuel Morse and Peter Cooper and a number of other well-respected and, more importantly, wealthy men. And on the table just next to the globe is a piece of cable, and he's got a map showing where he's going to run it. And this is not how it happened, but it was those people, and they had lots of meetings where they discussed what they were doing, and they invested money in it. But the problem was the cable couldn't be made in America, as Britain had the monopoly on gutta percha, which is the only material at the time that could be used as an insulator. And so cable manufacturing, which was then only a few years old, was centered in England. So Cyrus took the first of what were to be, I think, 35 or 40 voyages by ship across the Atlantic. And during the visit, he met John Watkins Brett, who had, with his brother, has succeeded with the 1851 cable. And he was probably at the time the leading British businessman in submarine cables. Field also had persuaded the British government to get landing rights in Ireland. And while he was there, he raised further funds from British industrialists. These included the Manchester cotton men, who imported a large amount of raw cotton from the American South to feed the mills, which covered the landscape around Manchester, as I well remember. And these cotton men, who were quite well-to-do, could see the advantage of knowing the price of cotton in New York at a moment's notice. And this was the route they proposed from Valentia in Ireland over to Heart's Content Bay in Newfoundland, which is about 60 miles from St. John's. Very nice little bay. And I've been to both those places, which is kind of neat. So where was Greenwich in all of this, though? Because we know that later Greenwich was a major player in the cable industry, but that wasn't quite yet. The Gutta Percha Company, which made those decorative items, was on Wharf Road, just off the Regent's Canal, and the building is still there today. They had an 1848 patent for an apparatus for covering or coating wire or cord to an infinite length with any plastic substance, which pretty well nailed down copper wire covered with gutta percha. So they had a virtual monopoly on insulating copper wire to make the cable core, which they did for quite a few years. Cable armoring in the early days was done by Cooper and Company with a factory at Morden Wharf. Glass Elliott was registered in 1854, but they didn't take over the Enderby Wharf site till 1857. And that was when they were awarded the contract to make half of the first Atlantic cable that year. And Newall and Company of Gateshead, who had developed the armoring machines, had a factory at Birkenhead, and they made the other half of the cable on the River Mersey at Birkenhead. And there's one oddity that happened here is that the lay of the cable wasn't specified because everybody knew which way you should spiral the outer armoring wire. You spiral it to the right. Well, you made it the same way as rope. But unfortunately, Newall and Cooper didn't liaise with each other on this. So they used opposite lay on the two halves of the cable. So when they came to splice it together, it would have unraveled, and they eventually had to use an elaborate wooden fixture to splice the cable so that wouldn't happen. So that was an odd thing. And this was the cable that they made. And while it looks impressive there, that's less than 3/4 of an inch diameter. And you can see that the core of it now has 7 copper wires instead of 1, which gives you some redundancy in case of any stress on the cable. And then gutta percha and the usual hemp around it, and then multiple stranded iron wires for the armoring. And they made 2,000 miles of this. The British government loaned the cable company HMS Agamemnon, one of the newest of the old wooden warships, and the US government provided its brand new warship, the USS Niagara, And Niagara had just been fitted out and launched. And when it got to England, they gutted it to put the cable stuff in. And you needed 2 ships because the 2,000-mile length of the cable, which weighed about 1 ton per mile, couldn't be carried on a single ship. So it split half and half between the 2 ships. So there's the Agamemnon on the Thames. Maybe able to recognize some of the buildings there, not far from Greenwich, loading cable. And here's the Niagara, which, even though it's a steel-hulled steamship, still has sails. And there's the cable fleet. And this is a nice lithograph showing the Agamemnon on the left and Niagara on the right with some of the support ships, just to give an idea of the scale. And each of these ships is going to carry 1,000 miles of cable. So it took 3 expeditions, one in 1857 and 2 in 1858, before the cable was successfully laid. There were many problems and near disasters along the way, including the cable breaking and being lost and tremendous storms in the North Atlantic. For the June 1858 expedition, the plan was to sail both ships to the middle of the Atlantic and splice together 2 halves of the cable. Niagara would then steam towards Newfoundland and Agamemnon towards Ireland. And of course, the ships would be able to send messages to each other over the cable while doing this, as is exactly the case today. You connect the shore end, and in this case, they're connected 2 ends on board ship, and you can then work the cable from the ends that are still inboard on the ship. And that was, of course, the only means of communication they had. So they set out for mid-Atlantic, but they had considerable trouble just reaching that point, the rendezvous point. A tremendous storm came up and the ships became separated. And during almost a week of strong winds and high seas, Agamemnon almost capsized. Finally, the storms abated and ships were able to meet up and start laying the cable. So while researching this expedition, I discovered an interesting example of newspaper exaggeration, which is by no means invented by today's tabloids and clickbait websites. On board the British ship, Agamemnon, was the mechanical engineer Henry Clifford, who was also an accomplished painter. He made drawings of scenes of the cable expedition while it was underway, and these were published in the Illustrated London News when the cable fleet returned. And he later made oil paintings from his drawings for his family and friends. And the National Maritime Museum has 4 of his oil paintings and a number of watercolors. But of course, if the Great Storm happened today and it was then the stories published in the newspaper, the headline would almost certainly be something like this. In June 1858, they tried to lay a cable across the Atlantic. You'll never believe what happened next. And this is the illustration that goes with it. Now, I don't know about you, but to me, that ship is gone. There's no way it's ever going to come back from that. But as I say, Henry Clifford later did paintings of some of his sketches. This is based on one of his sketches. And a few years ago, I visited his great-granddaughter in Devon, and she showed me Henry Clifford's own painting of this same scene, which came down in the family, based on his sketch that he did on board ship. And this is actually what it looked like in his painting. And while it's not bad there, it's certainly nothing, certainly nothing like this. Okay, so you can see the difference. So that's how it was reported, though. So there were further problems on this expedition, the first expedition of 1850. The cable broke, the end was lost in the depths of the Atlantic, and the ships had to return to port in England. But a second expedition a few weeks later was successful. The circuit was completed between Ireland and Newfoundland, and messages were exchanged between Queen Victoria and President Buchanan. This is a view of the telegraph room in the Newfoundland cable station, painted by one of the operators. And you can see the heavy cable coming up from the floor to the right of the fireplace and over to the workbench. And just above the cable at the left is the landline telegraph going out over the telegraph poles to carry the signal. So the operator here is taking the signals over the cable and then retransmitting them over the landline. And at the bottom right, you can see one of the very large induction coils. That thing is 6 feet long. It doesn't survive, although smaller ones do. And the idea there was to use a very high voltage to get the signal over the cable, which turned out to be the wrong idea. But this is one of the very few views we see the size of the induction coil that they thought would be the way to work a telegraph cable. So this was a problem. The signals were weak, messages had to be sent and resent. A lot of the traffic, which we have transcriptions of over the cable, was test signals and requests, please send again. And after about 3 weeks, the cable failed completely in early September 1858. And by the end of the year, it had been abandoned. The cable expeditions around this time were dogged by repeated failures, particularly in attempts to lay long cables, but each time more money was raised and more expeditions mounted. The 1858 cable worked for only a few weeks, and there was another expensive failure on a different route in 1859. Part of the problem was that insufficient attention had been paid to the design and manufacturing of long cables, and the operation was not based on any sound theory. As a result, the British government set up a committee of inquiry, a joint committee between the government and the cable company, who each had 4 representatives, and they met periodically for 10 months from December 1859 to September 1860. And they heard evidence from what must have been every scientist, engineer, and manufacturer who'd ever been involved in the cable industry. The result of the inquiry was an 80,000-word report, which I have a copy of. And this is a foolscap-sized document in small type, just packed with information. And this report was mostly on practical matters. They weren't looking to place blame. They wanted to know why the cables had failed. But the main goal of the committee was to say, what do we need to do to fix it? And this report was probably the first report of an industrial tribunal on a major failure. And the conclusion was that for the 1858 cable, failure was due to causes which might have been guarded against had adequate preliminary investigation been made. So in other words, if you put a bit more thought into it, it might have worked. But of course, the rush was to get it laid and recoup the investment. But despite its early failure, the 1858 Atlantic cable was a significant milestone. It showed that a long cable could be successfully laid and operated, and proved it could be financially viable. Because even with the cable's very slow transmission speed of just a few words per hour at best, messages sent by the British government to its commanders in Canada, countermanding orders for regiments to return to England, saved the government over £50,000, it's reported, which I calculate is equivalent to several million pounds today. And of course, the commercial possibilities of instant messages between New York and London were obvious to every international trader. And this report really marked a turning point and led to the beginnings of the modern cable industry. It was realized that you needed high quality materials, carefully controlled manufacture and storage. William Thomson particularly worked out a lot of the theory of signal transmission on long cables, and he, among others, developed instruments and techniques for efficiently sending messages. So by 1864, when new funding was raised for an Atlantic cable, the industry had greatly expanded, and there were now a good number of companies in the cable business on the Thames around Greenwich. So if we divert from the Victorian internet for a few minutes, and just take a quick look at some of those companies. So in preparation for making and laying the 1865 cable, Glass Elliott merged with the Gutta Percha Company to form the Telegraph Construction Maintenance Company, which of course everybody always calls Telcon. And they're at Enderby Wharf, where there's been cable business ever since, even today with Alcatel occupying the premises. Henley's originally shared the Enderby premises with Glass Elliott, but moved to North Woolwich, and they made submarine cables till the turn of the century, after which they mainly did just general electrical equipment and electric wire production. In 1863, Stephen W. Silver formed the India Rubber Gutta Percha and Telegraph Works Company Limited, which for obvious reasons, as with Telcon, was always called the Silvertown Company. And they made cables until the 1920s. William Hooper began making rubber insulated wires in 1864 and established Hooper's Telegraph Works in Millwall in 1870. And Siemens Brothers was formed in January 1865 with premises at Woolwich, which had been originally established by Siemens and Halske. And as we know, Siemens was there for, 100 years, over 100 years, although they weren't making cables there for that, all that time. So meanwhile, back to the Atlantic cable. The Civil War, of course, got in the way, which is why it took until 1864, 6 years after the failure of the 1858 cable. But by 1864, Telcom was in business, and when they were ready to make and lay a much improved cable, but they needed a suitable ship. Great Eastern had been launched at Millwall in 1858. And as we know, after many financial problems in passenger service, it was sold at a bankruptcy auction in 1864. The new owners were Daniel Gooch, Thomas Brassey, and John Pender, our old friend, who formed the Great Eastern Steamship Company, and they chartered the ship to Telcon to lay the cable for £50,000 of Telcon shares. Telcon then carried out the necessary conversion work on the ship and moored Great Eastern at Sheerness, ready to be loaded with cable. The 2,000 miles of cable were manufactured by Telcon at Enderby Wharf, and transferred to Great Eastern using 2 hulks loaned by the British Navy. And the expedition set out from Ireland in July 1865. And Henry Clifford, the mechanical engineer from the Agamemnon, had worked on the cable machinery, the cable engines on the Great Eastern also, but he didn't stop painting. And again, he did a number, this is actually a preliminary painting that I have in my collection, which he made on the 1865 expedition. And the National Maritime Museum has the finished oil painting of this. He was a very, very talented artist, and he eventually became Telcom's chief engineer, which he did until his retirement. So there was a setback in 1865. The cable broke just 600 miles from Newfoundland and was lost in 12,000 feet of water. But even then, it was obvious that complete success was in reach. A second Great Eastern expedition in 1866 not only laid the cable without incident from Ireland to Newfoundland in just 2 weeks, but then went out and recovered and completed the lost cable of the previous year, providing 2 circuits for messages between Europe and America. And the recovery expedition for the 1865 cable pioneered techniques and equipment for retrieving damaged cables from deep water, which I think are still in use today. At least the concepts are still in use, certainly. And the successful laying of the cable in 1866 was celebrated as the 8th wonder of the world. And ever since then, North America and Europe have been in permanent connection via undersea cables. And the early commercial promise was amply fulfilled by these cables. Messages were transmitted at 6 to 8 words per minute, and they were charged at $5 a word, and that's 1866 dollars. So very, very expensive. But if you understand that the alternative was a 6-week gap in communication by putting messages on a ship, this was worth a lot of money to the industrialists and the merchants. So, but of course, the advances in communications had come at considerable expense, and the cost of the messages wasn't unreasonable, but it really did restrict the service to commercial and government traffic. And other than for emergencies, the general public did what they'd always done, which was to write a letter. And this remained the case, particularly for international communication over long cables, until well into the 20th century. But despite the cost of laying a long cable, over $1 million at the time, perhaps several hundred million today, so about the same as laying a fiber optic cable, the high return on investment for commercial traffic led to a boom in cable laying worldwide. John Pender remained in the cable business. He'd been a cotton merchant, made good money there, but I think he realized that the new money, and I think greatly aided by his wife, who Stuart can tell us a lot more about, Emma Pender, he was one of the pioneering investors and was a key figure in the success of the first Atlantic cables. In 1870, he completed his own network of cables to connect Britain to India. And his Eastern Telegraph Company and its many subsidiaries eventually established a worldwide telegraph network. And as Stuart mentioned earlier, we're celebrating the 150th anniversary of the Eastern Telegraph Company, which has just passed. So more Atlantic cables followed, along with cables linking many other parts of the world. And the cable companies started to commission purpose-built ships. Before that, you saw the Goliath, which was just a tug with a small amount of cable. And Great Eastern was the largest ship used for cable laying, but there they just gutted it as a passenger ship and put in the circular holes known as cable tanks and really converted it to cable laying. But that had certain disadvantages. So purpose-built ships followed, and Siemens Brothers of Woolwich had cable ship Faraday built in 1874. And this had such an advanced design, it implemented many features that became common, that it remained in service almost 50 years. It wasn't scrapped until the mid-1920s when it was replaced by cable ship Faraday II. So by this time, getting into the 1870s, Siemens and Telcom were the leading suppliers of submarine cables worldwide, a position they maintained until their merger in 1935 to form Submarine Cables Limited. And the cable operations that was the cable operations of the companies. That was still based at Enderby Wharf. By the end of the 1800s, there were 10 Atlantic cables, with 2 more in course of construction, and 36 cable ships were employed in laying new lines or repairing the then 130,000 miles of cable already at the bottom of the sea. Many of the ships were fitted out with cable machinery by Johnson and Phillips of Charlton, another local company. And J&P were engaged in that business from 1882 until 1964 and fitted out a total of over 70 cable ships. So the fourth quarter of the 1800s was really a boom period. The Eastern Telegraph Company continued to expand its network, and in 1901, they published this map. Now, they did not own the cables across the Atlantic, which you can see in the center top there. But the rest of that network was largely their cables. And even in the Pacific, there were proposed cables in 1901. And you can see why they were called the Eastern Telegraph Company, because initially their cables went to the east to connect India at first, but then via rather circuitous routes, they connected Australia, New Zealand, and then there were cables all around Africa and South America, and Pacific cables were being planned. So this we could call the World Wide Web in 1901, certainly from an infrastructure point of view. And shortly after this map was published, those two cables were actually completed across the Pacific in 1902. And the two cables, one was under British control as part of the network, which eventually became the all-red network of British cables around the world. So that one actually followed one of the existing Atlantic cables, then landline across Canada, and then the new Pacific cable went from Vancouver Island over to Australia. And the American cable was landed near San Francisco and hopped across a number of these smaller islands that were American territories or to become American territories, including Hawaii. So the world was now really completely girdled. And the cable engineers, of course, had not been idle. One of the main concerns was the speedy and efficient transmission of signals over the cable, as this was directly related to revenue. There were continual improvements in the mechanical and electrical design of the cables, and automated transmitting and receiving equipment replaced manual operation. Remember, though, at this time, there was still no electronics. The valve or vacuum tube was only just being developed and wouldn't be in practical use for quite a while. So you're strictly sending electrical signals over a wire with just the power of your battery. And so they developed very sensitive receiving instruments, siphon recorders that would write with a pen on paper tape, amplifiers that weren't electronic amplifiers, they were electromechanical amplifiers, kind of like relays, but relays that could take the tiny signal coming off the cable and boost it enough electromechanically to get it over the next leg. So, but they also developed multiplexing, so a cable could carry more one message at the same time. And then, as I mentioned, the electromechanical relay, so you didn't have to re-key the signal, it'd be retransmitted. And by this time, talking the early 1900s, messages could be sent at about 40 words per minute. And of course, with all the competition, there'd been significant reduction in the charges, but the cable industry continued to be very profitable. But now we're in the early 1900s, an Italian guy comes on the scene, Mr. Marconi. And in 1901, it's generally believed that he sent the first wireless signal, SSSS, across the Atlantic. There's some disputing whether he actually received that immediately, because he knew what signal they were going to be transmitting and when they were going to be transmitting it. And the initial report was he had absolutely heard that through the static and the noise. So there are some doubters, but certainly very shortly after that, he'd had definitely established communication to Newfoundland. And how he did it at the Newfoundland end was with a kite. And this is from Signal Hill, which is called that still today. And there he's launching the kite with a long wire antenna. That's Marconi over on the left there. And that was the beginning, really, of radio communications. And ironically, in Newfoundland, the cable company still had a monopoly on communication, because Frederick Gisborne, remember him, he was going to start communications, and he got a 50-year franchise from Newfoundland government for any method of communications to Newfoundland. Even though radio wouldn't be thought of for the next 50 years, the cable company prevailed and forced Marconi to be ejected from Newfoundland. Of course, he just moved to Nova Scotia, just down the road effectively, and continued from there. And of course, he then worked on ship-to-shore communication. And by the end of the First World War, the British Post Office was working on using his transmitters as an alternative way to send messages around the world. And competition between cable and wireless became a recurring theme throughout the 20th century and continues today, about which I'll talk a bit more later. So the post-war period was a period of consolidation. There weren't very many new Atlantic cables laid for almost 30 years, but the technology continued to improve, and repairing deep sea cables have become routine. Here's Her Majesty's telegraph ship Iris. And this really looks like a fairly modern ship at this point, even though it's now close to, let's see, when was that built? At least 80 some years ago, probably 90 years ago. But Even for the early cables, though, before you laid a cable on a new route, you'd need an accurate survey. I mentioned that Matthew Fontaine Maury had surveyed the bed of the Atlantic, and that became a routine procedure. You dropped a sounding line, you checked the depth at intervals, you had a little glass tube on the end which could bring up a sample of the ooze at the bottom so you could get an idea what the seabed was like. And the survey was made and recorded on the chart. And the chart was then used for the cable laying ship to track its route, which they followed as closely as possible. Of course, they'd mark any variations to the nominal route. They'd also record the ship's position, the length of cable paid out each day. And then if a fault occurred after the cable went into service, you could measure the electrical characteristics of the cable from both ends, and you could then locate the position of the break fairly accurately. And that section of cable could then be recovered and repaired. And even the occasional faults in fiber optic cables that bring down the internet in parts will fix the same way as they were from the beginning of the industry. You locate the fault with tests from each end, then you send out a repair expedition. And even major problems such as the damage to the Tonga cable are nothing new. In 1929, an earthquake in the Grand Banks off Newfoundland broke 12 transatlantic telegraph cables, which was pretty well all of them at the time. And the companies, the competing companies banded together and sent all their repair ships out and worked collaboratively to put them all back in service. And fixing faults, I think it's probably still done more or less the same on fiber optic cables as it was in the early days. Is a copper cable from I think the 1940s being repaired on board ship. So the way you fix a cable is you can't send a submersible down in deep ocean because A, it's difficult to get down there, witness the expeditions to Titanic, and B, you couldn't work down there. So what you do is you grapple for the cable by trawling the ship across the line of the cable with a grapnel until you hook it. In many cases, a cutting grapnel was used, which would cut the cable and haul one end of it up, because otherwise, with the relatively small amount of slack, if you tried to haul the whole thing while it was still connected, it would break anyway. So you would haul at one end of the cable, test it to shore, see if you got the good end or the bad end. If you got the good end, you'd put it on a buoy and sail down in the opposite direction, haul the cable up again, cut it there and check it to shore. And if you now have two good ends, you'd splice on a new piece of cable from your stock, sail back to the buoy where your first end is, splice it together, and drop the cable overboard. And of course, the splicing had to be done on deck because you had to have both ends of the cable and you had to be able to get them offshore again. It's like building an aeroplane in your garage, otherwise, if you tried to do this under any significant cover. And fiber optic cables, while the jointing is a bit more technically advanced, you still need to get the two ends of the cable together, match up the conductors, either copper or fiber, join them together in a way that the signal path will be uninterrupted, and then recoat the cable with protection before you put it back down again. So back to cable and wireless, though. By the 1920s, there was quite a lot of competition, which of course drove rates down. And there was a possibility that both the cable and the wireless companies could get into financial trouble. And the British government was concerned that they might then be taken over by foreign entities, as they were both private, they were all private companies, they were not government owned. So that would result in a loss of imperial communications control. So in 1928, Pender's Eastern Telegraph Company, which is now the Eastern and Associated Telegraph Company with all his subsidiaries merged into it, they merged with the Marconi Wireless Telegraph Company to form Imperial and International Communications. And the government had a controlling stake in this. And some years later, a few years later, this would become Cable and Wireless, oddly enough. The same Cable and Wireless today, although they don't really do this kind of work anymore, I don't think. And both the radio and the cable interests benefited from the collaboration. Of course, once radio came along, people said, oh, well, cable will be obsolete now. But cables had an advantage because radio transmissions, particularly in those days, were insecure. So you couldn't send secret messages. There were codes you could use, but easily cracked. So cables continued to prosper. And there was an important technical development in the 1920s, which was the use of mu metal. And this is a little bit of a technical thing. The problem with sending a signal on a cable underwater is that the electrical field created by the signal passing through the copper escapes through the outside of the cable, interacts with the seawater, which then reacts as electromagnetic fields tend to do. And it caused an effect which the early engineers called retardation, which meant if you put a dot in the end, which is a sharp pulse, you would get a sharp beginning to your pulse, but then it would fade away slowly. So if you then tried to send a dash, which is 3 times long as a dot, you couldn't discriminate between a dot and a dash. And what they worked out was you would send a positive voltage pulse for a dot and an equal negative pulse for a dash, and those you could make out at the end of the cable. And the loading was a way of putting a metal wrapping around the conductor, and that would then reverse the effects of the retardation to a large extent, and you could increase the working speed of the cable. And of course, it gave you a rather more complicated cable, but and you needed a special mu metal, they called it, wire, which would have the right characteristics electromagnetically. And so they made these loaded cables. The overall construction is still the same: the copper in the center, gutta percha, padding, and then the steel outer armoring wires, but just with this extra layer involved. So, but still, this, while it increased the speed of the cable, this was only for telegraph messages. And we're now in the 1920s, and the first radio service, voice radio service across the Atlantic for commercial use was opened in the mid-1920s. So now if you wanted to make a phone call, you could do that by radio. Now it's shortwave radio, of course, which is at the best of times fuzzy and distorted and all sorts of interference, but you could make it an instantaneous phone call. You had to book it, and there weren't very many circuits, and it was very expensive, but again, it was worth it to people that needed it. And telephone wasn't new to cables. As early as, I think, 1891, the first telephone cable was laid across the channel. But again, long lines were much more difficult than short lines. And once you get up to about 100 miles, you just cannot get a voice signal through a cable. You just don't get anything out the other end. There's nothing you can do about it. So what you need to do is amplify the signal. And how do you build an amplifier into a cable that's underwater and is 2,000 miles long? And not just one amplifier. They worked out you need an amplifier about every 20 miles. So if you wanted to lay an Atlantic cable, say from Scotland to Newfoundland, you needed 2,000 miles of cable. You needed 100 amplifiers in there. And while transistors had been invented, we're now getting into the 1950s, transistors weren't considered reliable enough. So they used vacuum tube amplifiers. And this was a collaborative work. They were looking to lay a transatlantic telephone cable to be open for service in 1956. And it was the British Post Office, the Canadian Overseas Telecoms Authority, and AT&T in the States. And they collaborated on the design and production. And AT&T, of course, was Bell Labs, who had probably the best research engineers, physicists, mathematicians in the world at that time. And they designed a vacuum tube, which was tested, and they came up with a vacuum tube that would be reliable for what they believed to be the entire possible working life of the cable, 20 years. And they built these repeaters or amplifiers. And, you know, we're not talking a tiny thing. These are probably a foot in diameter by 6 feet long, that kind of range. In a steel housing, it could withstand the depths of the ocean. And the cable came in at each in one end and out of the other end. And of course, you had to power them. So how do you power them? Because how do you get electricity down your tiny bit of copper? You know, if you've seen big electrical cables that carry high current, they're, you know, 1/2 inch diameter. So they designed the system to work like Christmas tree lights. You know, you plug in the string of Christmas tree lights, and if one of them goes out, the whole string goes out. But what it means is you can run multiple devices, each taking only a small amount of power, by stringing them together in that method. And of course, they built in a bypass. And what they ended up doing is putting 2,000 volts DC in at each end of the cable. And each of the 100 repeaters took its 40 volts from there and the appropriate current. And they were able to run these powered amplifiers for the length of the cable. And here's TAT1, Transatlantic Telephone 1. And you can see the design has not really changed much in 100 years. You've still got the copper in the center, which is the signal wire. There's another copper layer. You got the insulation now polyethylene rather than gutta percha. Another layer of copper, which is the power conductor. And then the rest of it is just padding and protection out to the armoring layer. And so this went into service in 1956. And the repeaters were very clever, but they weren't clever enough to transmit the signal in both directions. So they actually laid 2 cables, an eastbound cable and a westbound cable. And with all that work, you could actually make 36 simultaneous telephone calls. And in fact, one of those telephone channels was able to replace all of the telegraph cables that were carrying telex messages across the Atlantic by that time. And in the early 60s, pretty well the entire worldwide telegraph network shut down because it was replaced on long circuits by these new cables. And you needed one cable instead of 10. But again, expensive. I believe a call cost about £6 for 3 minutes, and probably about £60 for a 3-minute call would be the equivalent today. So just 3 years later, they laid transatlantic 2, TAT2, using basically the same technology. But again, the engineers have been working and they came up with what they call the lightweight cable. And the lightweight cable, as you can see, TAT1 has that armoring on the outside. The lightweight cable, you can see again the copper in the center, but then the steel stranded wire in the center. And again, the copper right before the insulation to carry the power. But then the outside is just polyethylene out to about 1 inch or 1.5 inches diameter. And it's called lightweight cable because you don't have that huge weight of steel on the outside. This can only be used in deep water and near the shore. Same with fiber optic cables. Near the shore, you would use the same kind of armoring. So those machines that we saw from the early 1850s are still in use today. I saw them at the Simplex factory, now TE Subcom up in New Hampshire a few years ago. Machines from the 1950s doing exactly the same job of armoring the cable. So this was Cantat, the Canadian transatlantic telephone cable. And this was the first link in a Commonwealth round the world cable laid between Scotland and Newfoundland. And this also had bidirectional repeaters, so you didn't need 2 cables. And this became the standard for copper cables for the next 17 years. So again, progress was rapid after this. Further Atlantic telephone cables followed at short intervals. In 1966, just 10 years after the first one, which had 36 channels, TAT6 had 4,000 telephone channels. But now what about satellites? Everybody says, well, doesn't everything go by satellite these days? And of course it doesn't. Only about perhaps 1% of the traffic goes by satellite, and everything else is on fiber optic cables. So, but radio made a comeback in the 60s because you still didn't have very high bandwidth copper cables. They could carry 36 telephone calls, but not television pictures, for example. So geostationary satellites, because what you need a satellite that's stationary in the sky relative to the rotation of the Earth. So you can point a big dish at it at each end, and it's always going to be where you expect it to be. So that's called a geostationary satellite. And they were actually proposed by the scientist and science fiction writer Arthur C. Clarke in 1944 in an article in Wireless World. Although unfortunately, he couldn't patent the idea. And the satellites are 22,000 miles in the sky, like this. And they have to be at that height to remain apparently stationary. But that's also the problem, because being 22,000 miles up in the sky, even with the radio waves to them traveling at the speed of light, there's a delay, a round trip delay. And if you look, it takes 125 milliseconds to get up there and down to your other station. And then the reply comes back the same way. So 500 milliseconds, a half second. And that's the half second delay that you hear, sometimes worse, when somebody's on a satellite phone out in the field reporting perhaps. And that's because it's going by satellite. And that would really bring the internet to its knees at this point. So that was why cables persisted. So as I said, the round trip hop is 88,000 miles, half a second. And so that was a disadvantage of satellite communication. Also lack of security, again, because anybody could receive those signals. You know, back when they started satellite television, you just put up a big dish, and before they encrypted it, you could tap into the satellite TV signals. And while they were faster than the copper cables, it turned out a little bit later that they weren't faster than fiber optic cables, and then eventually they weren't faster by a long way than fiber optic cables. So at this time, we're in the late 60s, and there's quite a lot of satellites going up. But now people are starting to think about fiber optic cables, which were developed first for land use, as with everything else. So in 1980, for example, STC in Britain performed trials of a 5-mile loop of fiber optic cable at Loch Fyne in Scotland. Oddly, the location of John Pender's summer house for the cable connection from 100 years earlier. There's a fiber optic cable on the left, and on the right is one of the fiber optic repeaters, similar to the copper cable repeaters, but designed to handle optical traffic rather than electrical traffic. And again, it gives you an idea of the scale of the repeater. And about the same time in the USA, Bell Labs again and Simplex, who was the major American cable maker, set up a joint venture in 1976 to produce the next generation of transatlantic cables. And they were planning for TAT-8 by this time. And that was scheduled for 1988. And we're still only in 1976 at the moment. So they're thinking well in advance. And that was planned to be the first fiber optic Atlantic cable. So during this period, Simplex made several lengths of test cable. And meanwhile, Bell Labs was working with Western Electric, who designed the vacuum tubes, or produced the vacuum tubes and a lot of the repeaters for TAT-1 some years earlier. And they were building an integrated circuit-based optical repeater. So we've now gone from valves to transistors to integrated circuits. And by August 1982, a small system was ready for Bell Labs to test. And they had their cable ship Long Lines, part of a division of AT&T that laid cables. And they had 18 kilometers of lightweight fiber optic cable, which you can see a slice of there. And this is a souvenir paperweight. They had one repeater, and they took it out to the deep ocean off Bermuda, and they laid it. They tested it from end to end. They said, well, that's great, but can we haul it up again? And they hauled it up and tested it from end to end, no problems. And they said, okay, well, conceptually, this is going to work. Now, all we have to do is go from 18 kilometers to 3,200 kilometers across the Atlantic. So they took the 18 kilometers of cable back to Bell Labs in New Jersey, to their Holmdel facility, and put it in the basement in case they ever need to refer to it. So this was 1982, so 40 years ago this year, and it's still there. In November last year, I had an email from the company that now manages the facility. It's now called Bell Works because Bell Labs went through many transitions after the breakup of AT&T, and this building was surplus, huge building. And it was bought by an entrepreneur who's converted it into a tech center. It has a theater there. It has shops and stores. And it has a basement they haven't done anything with yet. And in the basement is 18 kilometers of fiber optic cable from this test. And so I spoke to the guy and he said, why don't you come out and see it? So I went out there and I sawed a length off. He very kindly had one of the engineers there saw a length off for me. And this was the very first production fiber optic cable in the USA, and they call it the SL Light Guide cable. And you can see the still familiar design. In this case, as you can see from the diagram, the wire down the center is just for structural purposes, and wrapped around that are 12 fibers in elastomer with a nylon jacket. And then the same thing as the other regular lightweight cable, the stranded steel, the copper for power, the polyethylene to insulate it. And this is what they call their light guide cable. So in 1988, they laid TAT-1, and a year later, Tim Berners-Lee came along and invented the World Wide Web, and everything began to change. The internet, the underlying system on which the World Wide Web rides, had been developed beginning in the late 1970s, but it remained largely a research and educational resource material accessible to only a few, and mainly scientists. As the 1980s progressed, the market for personal computers expanded from hobbyists to the general population. And by the mid-1990s, PCs found their ideal application in the World Wide Web. While undersea cables provided rapid communication around the world for well over 100 years at that point, the rise of the web would soon spread the desire for fast connections to millions of new customers, an unprecedented leap which has had a significant impact on all our lives. TAT-8 in 1988 had 40,000 telephone channels, and it remained in service until 2002. It was followed by 20 more Atlantic cables and many other cables worldwide. There were further improvements in optical transmission, which were introduced in 1996 for TAT-12 and TAT-13. And despite the financial recessions after that, cable capacity has increased exponentially in the 34 years since TAT-8. And for all practical purposes, there's really unlimited bandwidth to almost every part of the world, unless you have an undersea volcano, of course. So in today's cable communications era, the primary traffic, of course, is no longer voice and text messages, it's raw data, and everything is carried digitally. Phone calls, emails, web traffic, video, financial data, everything really. Cheaper and faster than satellite circuits and with higher security. Cables can't be tapped on the seabed without cutting them, which is immediately obvious at both ends. They can be hacked, but you need access to the head end stations, the shore end stations, which it's believed that certainly the British and American governments have. So nothing anywhere is secure really, but it's immune to casual hackers as far as the cable itself is concerned. But despite all these changes, many things have stayed the same in the 170 years since the first cables were laid from England to France. As we can see on here, cables still have a conductor to carry the signal, glass instead of copper, an insulator to protect the circuits against water, polyethylene instead of gutta percha, and a strength member, steel instead of iron. So here's a cross section of the first Atlantic cable. And this is to scale, by the way. You know, people say how big a fiber optic cable, and some people they're 3 inches. No, they're literally less than an inch for deep sea fiber optic cable. And looking at the cross section again, in 1858, you can see the 7 copper conductors in the center, the gutta percha, the hemp packing, and the iron wire for strength and protection. And the fiber optic, the fibers in that center, the little oddly lit fibers, because that's how my scanner sees them. They're in a plastic tube, so they can move a little bit as the cable is flexed. That's the little white ring around them. The stranded shield for strength, the copper to power the repeaters, the polyethylene for insulation. Exactly the same concept, just different technology. And of course, today, cable routes are surveyed with satellite navigation instead of celestial, but the cables are still laid the same way. You pay them out from a ship while steaming ahead. You use a cable engine similar to those devised in the 1860s to regulate the paying out speed. Repairs are made as they always were. You haul the cable in, you splice it, you repair it as necessary. Cable ships really look very much the same from the outside, but of course, they have all the benefits of modern marine and electronic technology. There's another view of the cables from the side, same ones we were just looking at. And here's a reasonably modern cable ship, the Global Sentinel. And one final note on communication satellites, back to radio again. These, of course, are still the only way to provide internet service to rural areas and underdeveloped areas. But the time lag is the problem. So what's the solution? The solution is to use a lower orbit, but then the satellites are no longer synchronous. They're flying past. Occasionally here, I can see the International Space Station. There are sites online where you can track its path and it says, go outside, look in this direction. And I've done that a couple of times. And when the orbit brings it over my house here, and it moves across my entire field of view in just a few seconds. And that's in low Earth orbit. And that's how fast the communication satellites would go past if they're in that orbit. So if you're going to do that, you need a large number of satellites in the same low Earth orbit. And Elon Musk had this idea not long ago with his Starlink. And the trick here is you've got a lot of satellites, tens of thousands he plans eventually, but you can only see a small number of them at any time as they fly by. So what they have to do is hand off your communications to each other and to everybody else so that you retain a constant signal, but because they're in a fairly low orbit, you don't have the huge time delay. So they're orbiting about 300 miles above the Earth. And of course, this makes it fairly easy to service places where you can't get to with a wide connection. But of course, there's still a problem, and here it's bandwidth. How many users can you have at the same time? And in order to handle the logic of the communications, the system divides the Earth into service areas, and you can only have so many customers in a service area. It's like if you had too many people in a cell tower area, which in a disaster, and everybody tries to call it, sometimes you find cell service goes down, you might get a text message to you, but that's about it. So if you have too many customers in a given area for Starlink, it becomes ineffective. So where I am in suburban Long Island, not far from New York City, this service just wouldn't be practical for all the people who would like to use it. But if you're in the middle of nowhere where you have maybe dial-up if you're lucky, it's a great solution. But so really, most of us that have broadband connections are probably going to stick with them. No matter how much we hate BT, Virgin, and here Verizon and Altice, it's what we've got and it's the best thing. But as for the future, because of the inherent limitation of satellite communications, I believe cable will always be the backbone of the global network. Land-based fiber optic technology will continue to expand high-speed delivery of data, audio, and video direct to the end user, fiber to the home, which many of us have now. Starlink will provide service to remote areas, and wireless lets us connect the internet and make phone calls via Wi-Fi and cellular connections. But undersea cables, I believe, I don't see any way they won't continue to carry the bulk of the traffic around the world, the backbone, in other words. And Stuart's been working on a project you can't tell as much about, which is Google's Grace Hopper transatlantic cable, which I think is the most recent cable. It's just going to service now. It has 32 fibers, and each circuit needs 2 fibers. So there are 16 fiber pairs, 16 circuits in there. Each fiber pair will carry 30 terabits per second of data. So that's 480 terabits of data, which is half a petabit, I think is the next one. It's a term we're not even familiar with yet, but Google's new cable is up there. And Stuart tells me that over the life of the cable, there will be improvements in the transmission methods that using the same infrastructure will give us more capacity. So really, we have limitless bandwidth at this point. And here's the World Wide Web right now. This is a company called Cellular Geography that provides services to companies laying and maintaining cables. They very kindly make their maps available. And again, you can see, if you look at the Atlantic Ocean in the middle there, it looks almost exactly like it did in 1900. All those cables across the fiber optic, and the routes to the east and down Africa. And then, but the Pacific, you can see the expansion in the Pacific from those first two cables in 1902 to a vast number. It shows you where the business is now as well. So that's the World Wide Web in 2022. But so did all this begin as a Victorian internet? In some ways, the answer is yes. But unlike today's internet, the 19th century cable network was too expensive for most ordinary people to use for personal telegrams. But the commercial and technical success of even the early cables, especially the Atlantic cables, proved to the 19th century entrepreneurs and engineers the viability of a worldwide communications network that was open to anyone who wanted to pay for its use. And they built it. And I hope you can see from what I've discussed today that there's a direct path over the last 170 years from their copper cables to our glass ones. And despite inroads from competing technologies, subsea cables have always remained the reliable basis of global communications. And that's where we are today. Thank you, everybody.
Thank you, Bill. That was great. Absolutely wonderful. Thank you.
I will put my poster.
Oh, there's you.
Thank you to my good friend Alison Scott for saying, you need a poster. Do you have a good photo I could use? And that's me holding a piece of the German transatlantic cable made by Telcon in 1902, and a Telcon logo shirt provided by my good friend Jim Jones in Greenwich. And my creative friend Alison turned that into a really fabulous poster for me. So that's the Victorian internet to today's internet.
Was that a bit of the cable that was cut in August 1914 by the post office? Yes, the First World War broke out.
This was the one. In fact, I've got a great oral history from a guy, and he died, I think, in the late 50s, but he had actually worked at Coney Island, not far from here, for the commercial cable company. He did all sorts of techie things. He was a British guy, moved to America, and he worked for the commercial cable company. In the 1950s, a member of his family had an early tape recorder, and he gave him some of his memoirs, and he tells the story of how he was chatting with the operator in Germany, and the cable went dead. And he was actually on the circuit when the Brits cut it, amazingly. And this is a factory sample. But a few years ago, I had an email from a guy on Long Island who said, he told me his son was a commercial fisherman, and he'd hooked some cable off Coney Island. He couldn't tell me where, because of course, fishing grounds are kind of sacred. But he said, I've got a length of it. Come out and see me for lunch, and I'll give you a piece. So I went out to see him for lunch, and he said, well, can you tell me what it is? And I said, well, let me check a few things. And looking at the design of the cable, I could see it was almost certainly this one. And when I compared the sample he gave me with the factory samples, I could tell him definitely your son hooked a piece of the 1902 German Atlantic cable from Emden in Germany via the Azores to Coney Island, New York. So that was kind of neat. But this is part of the factory sample. So.
And you were showing some modern cables, and if I can hold that up, there's an Alcatel-Lucent cable that I was given by, what was an Alcatel-Lucent, when they were given the Queen's Award for Industry about 10 years ago. So
very nice.
And if you can see it end on, it's just like it showed. The actual fiber is in the middle. It's about 2 or 3 millimeters across, and then there's insulation and there's reinforcement, and the whole thing is what, 25 an inch diameter.
Yeah, that one of course is armored to go at the shore end, you know.
Yes.
Yeah. So
and actually somebody said, what is the, let me go back on the questions.
Oh, yeah, I haven't looked at the chat
typing questions.
Too busy talking here.
Yeah, okay. No. Somebody said, This is Roland said, is it possible to bury all of today's submarine cables to avoid them being trawled up or grappled by undesirable foreign navies? Well, I
Yes,
guess it's the cost, isn't it?
yeah, but it's like anything else. You can do it to where it's most logical to do so. Remember, I mentioned the lightweight cable is unarmored because it's mostly in deep sea.
Yeah.
But at the shore and it's armored. But there's also a device called a cable plow, which is about the size of a camper van. To correct me if it's a bit bigger than that, but somewhere in that region. And you have it on a gantry on the ship in a crane, and you haul it out and you feed the cable into what they call the bell mouth on the ship side, and it goes through the bell mouth down through the machine out the other side. Okay, then you lower it to the seabed and you tow it, and it's a cable plow. You tow it through the seabed and it digs a channel, puts the cable in it, and backfills it, depending on the terrain, of course. So I believe that's routine procedure near shore, perhaps out for a mile or so, depending on the terrain. And there are various ways of protecting the cable onshore to various conduits they can use. But in general, the majority of the cable is in the deep ocean. And the worst hazard there is in the offshore, where you're not too far offshore and you get a trawler, or more often a trawler than an anchor, I think, on fishing boats. They drag the trawl across the cable line and they hook it.
There was a notorious case a few years ago when a whole bunch of cables just off the coast of Alexandria in Egypt in the Mediterranean all got cut in within a few hours. And it was somebody dragging their anchor either deliberately or accidentally.
Yeah, I think they drag it now. I believe under international law, if you foul a cable and all the routes are marked and you've got to check on your charts, you are supposed to cut away your gear and you'll be reimbursed in full for any lost gear. But if some guys just say, well, let's just run for it, and they just keep dragging and break the cable, and then they escape with all their gear and keep fishing.
Of course,
that's a very, very serious offense, apparently.
Yeah, these days, of course, you can see which ship is where.
Yes.
David Hilton says, when laying the cable at sea, how do they splice the cable together to make a joint with structural integrity and longevity? Did they use some kind of jig? And how would they make the joint as waterproof and well armored as the rest of the cable?
Right, it's probably a little hard to see on that deck scene that I showed. But basically, it's like splicing a rope, except you're working with steel wires, maybe 3/16 or more of an inch diameter by times 12 or 14 wires, wrapped in sometimes double. So what you do, you have a tool which unwinds them for you. So you've got the cable, now if you're on board ship doing repair, you've got two good ends of the cable that you need to splice together. Okay, so you unwind the armoring back for a foot or so. So now you've got it just sticking out neatly, as if you had unwound the outer coating of a rope. And now what you've got the insulation. And again, I'm talking about the armored cables, the copper cables, okay? And you then cut away the insulation. So now you're down to the conductor. And what you would do, you would cut the conductor back for 6 or 8 inches on each piece. You'd make a long scarf joint on it, okay? Long angle joint, maybe over 3 or 4 inches. And you would whip fine iron wire around it and then solder it together, okay? So you now have a soldered joint. And in fact, Telcon apparently used to issue a sample of how to do this, an instructional case. Imagine a case about 15 inches long by 9 or 10 inches wide by 2 inches deep, and you open the lid and it's got the instructions. And then in the bed of the case, there's a sample of each of the cables at every step of this. And there's, I think, 12 different samples from the bare copper wire, scarf jointed, whipped with wire, soldered. And then what you do is you take gutta percha, and you've got a gutta percha sheet. Now remember, gutta percha is thermoplastic, so you can warm it up and then wrap it around the cable. So you form it around the cable and you seal the joint with a warm iron, and then you wrap another piece around with the seam rotated 120 degrees, and you'd seal that and a third piece around. So you now have 3 pieces of gutta percha, and you've sealed the ends as well, of course, where it joins the existing gutta percha. And then you put another coat around the whole thing, and then you start wrapping your iron wires back around it. Use hemp or manila wrapping around that for packing. And you have what they call a serving mallet, which takes the wires and brings them back into the spiral wrap. And you splice them like you splice a rope, except you're doing it with steel wire. Fiber optics, the same thing, but in deep water, it's a bit easier because fiber optic cable doesn't have the armoring on the outside. It has that stranded wire in the center. And then when you get down to the fibers, very nicely, the cable makers have color coded it for you. So I visited the TE Subcom factory in New Hampshire, and in what they call the dry plant, where they make the shore end equipment and they make the fiber core. You had to put on, clean wear, and said no photographs. And they took me around to see what they were doing. And the fiber comes in from Corning on 30-kilometer spools, which are about a 6-inch diameter spool of fiber. And they got as many spools as there are fibers in the cable, and each one is a different color. And they come out of a stranding machine, effectively. They go into the little plastic tube. So now you've got all your fibers in the tube. That then goes through the wire stranding machine that wraps the steel stranding around it. So you're out at about a 1/4-inch diameter now. Exact same technique, but on a smaller scale. And then they take a copper, flat strip of copper, and they have jigs that wrap it around into a tube. And the seam of the tube is soldered on or welded on the fly as it goes past. And what you end up with is something that's still about a 1/4-inch diameter. That's the core of the cable that they coil up. And then they put polyethylene around, the extrude polyethylene around it. So taking the reverse of that, if you need to repair it, you work your way back through the layers, and you have a jig that you put the fiber in, and they actually cleave the ends of the fiber. You think, well, how do they cut the fiber clean? Do they use a diamond saw? They actually use a diamond V blade, and they chop it. And apparently the way the glass is designed structurally, that gives you a clean, optically perfect square end. And you laser weld the ends together, matching color to color. And then you reverse the process to put the integrity of the cable back together.
And that's what they will be doing off the coast of Tonga. You mentioned volcanoes in your talk.
Yeah.
The Tonga cable that goes from Fiji to the island community of Tonga, which was destroyed by the volcano about 4 weeks ago now, mid-January. And the ship is now on site.
Okay.
Site at the weekend, they've discovered that 80 kilometers of that cable, and that's an 825 kilometer long cable. So about 10% of the cable has just been totally destroyed by the volcano.
Wow. I mean, usually they'd expect a few hundred feet of it, perhaps, on a bad day. Yeah.
So they need more cable. So
wow.
They're either going to call on the stocks that they've got on the board the ship that belong to other companies, or they're going to have to go back to Samoa to get some more cable. So it's going to take it's going to probably take another week or so for them to repair it, but it's a long process. And then they've got the branch cable that goes to the other offlying islands. So it's a long process, very expensive. Now, Roland says, when were the first repeaters used? I think you might have mentioned that, but when did
I mentioned a lot of things. So you remember I was talking about the sea trials in 1982, where they tested the repeater and the fiber underwater in deep water for the very first time. And they were planning for TAT-8 in 1988.
Yeah.
So there were shorter cables in service before that, but the first Atlantic cable was TAT-8 in 1988. And from there on, they just kept going. Everything was fiber after that. All the long cables were fiber.
David Hilton again. With the cable laid in deep water, was there any difference in the transmission rate possible between a cable operating in the open air and one operating in the extremes of temperature, pressure?
Yes, very good question, actually. Yeah, and Bell Labs wondered the same thing. Okay. Now, Bell Labs having infinite resources, and I saw I was out at Holmdel, and of course the building was an Aero Saarinen building. It is several 100,000 square feet. It's the most amazing building. They were going to demolish it and turn it into a giant housing. It's on 400 and some acres. And fortunately, that deal fell through, and an entrepreneur bought it. They bought the whole site for, I think, $29 million, the building and all the acreage. He sold off enough acreage to build some Mac mansions to recoup his base investment, but he still needed a huge amount of money to restore the building. And he got an angel investor to help him with that. And they turned it into Bell Works, and they've been working it for quite a few years now, but they've done an amazing job of it. But on site, when I went there, they said, do you want to see the ocean simulation facility? And I said, oh, absolutely. And this is the building on the perimeter of the site. And they built that specifically for the cable they were designing in the late 70s, early 80s, the one we saw the sample of, where they have it in the basement there. And it's not quite derelict now, but it's in very rough shape. And with this, they had high pressure tanks that they could take up to 100 meters of cable in, coiled, and high pressure pumping engines. And the big control panel is still there, probably 8 feet high by 12 feet wide. And then there's a room full of asbestos-clad pipes and engines and pumps and a partially flooded basement. Not a big building, it's just a single-story building. But it's still there and it hasn't been demolished. I hope it won't be. And that was specifically to test. So I found a technical report from some guys that were testing fiber. And they said that the change in the transmission capability of the fibers, whether individual fibers or in the cable, were within the errors in measurement of the equipment. So they were within the margin of error of the measurements. So there's no significant effect in the deep water. And they tested down to about 15,000 feet depth equivalent.
Excellent. Alison Onslow says her great-grandfather was with Siemens, involved with laying the cables to South America, amongst other things, 1880s onwards. Will this recording be available to viewers to revisit? And yes, it will. This is being recorded. I then have to edit it and put it on to YouTube. It's been a fairly clean presentation. I mean, there haven't been any technical glitches and things like that, so it shouldn't take me too long, but I've got a backlog of things to do and my day job as well. So Alison, it will be up there as soon as possible. So
in the meantime, Alison can go to my website, atlantic-cable.com, and just type Siemens into the search box, and there's a wealth of information there. Stuart and I have done a lot of work on Siemens history, and some of the results of that are there too.
Excellent.
So,
I could add to that, by the way.
Go on, Stuart.
Bill and I have written a draft book on the career of the
Faraday. Yeah,
Faraday.
Right.
Covers the 50 years which that lady's family must have been involved in. So
yeah, 1874 to 1924. Yep.
Yeah.
Mm.
Yeah, it was all about the cable operations they went on. So there's plenty of information available.
Excellent. Alan Essex says he recalls reading that old spent cables were being recovered for their copper content. Does that actually happen?
Yes, it does. Yeah. In fact, Stuart has friends who I've met also that have a business doing that. And I also know a guy up in Nova Scotia. Typically, you start with the shore end because that's where it's fairly easy to recover. In fact, there was a guy in Ireland, after all the cable stations closed in Ireland in the 1960s, he went out and hauled up all sorts of bits of cable, and every last one of them, no matter what they were, he sold as First Atlantic Cable. And you find them mounted on very nice Valentia slate still, and they're all listed First Atlantic Cable, and they're all over the place. I don't think any of them are the First Atlantic Cable. But anyway, yes, you can haul it up. In fact, the chap in Nova Scotia will say, I got a possibility on such and such a cable, like Cantat, for example, one of the ones I mentioned, one of the lightweight cables. He said, what was the exact cable type on that? And I look in the records and I say, oh, okay, good. He says, that's 17% copper. I can afford to bring it up. Because at that time, with the price of copper, it was worth bringing up because the weight of copper was over a certain amount. Because what are you going to do with the rest of the cable, the steel wire, the insulation, anything else? You know, it's scrap and you've got to pay to dispose of it. But now it turns out the very high quality polyethylene they use, because fiber has no recycle, but the polyethylene, it's the finest polyethylene. And even after it's hauled back up, remember, polyethylene, again, is thermoplastic, so very easy not to recycle, but to reuse. You just melt it down again, purify it. So the polyethylene can be sold as next grade polyethylene. And that's worth more than anything in the modern cables, unless you're up a length of fiber complete and sell it on the black market, of course, which has happened.
Yes. Okay.
Alan, I can add some more to that story. When cables went out of service in the early days, they were just abandoned on the seabed. And obviously, it became less and less easy to find good routes, especially coming into countries like the UK, where we had obviously a lot of links. And in the late 1980s, early 1990s, the Crown Estates, whose license you need to land a cable in the UK and operate it, changed their policy. And if you turn it from then on, if you turn a submarine cable off, you have to, under your license, recover it out to the 12-mile limit. And that should be in your cost base.
Wow.
So these companies that pick up cables for a commercial benefit are really looking at the cable beyond the 12-mile limit. And what the British have done, almost every country in the world is now following.
Right. Interesting.
Okay.
I know if, like, just one final comment, and I know we're running a little late, but off Nova Scotia, there are many, many old cables off Nova Scotia. Stuart said almost all abandoned in place, hundreds of years, 100 and some years old. And they were laying a new cable from Nova Scotia to reduce the time delay, because you can send a radio signal up from New York and gain a couple of milliseconds on a transatlantic cable. But they crossed the line. I was emailing the guy on board ship, and he contacted me and said, we're running through a lot of cables. So I identified some of them. And I think they crossed 16 different cables, 20 some times off the coast of Nova Scotia. And they needed to try and identify all of them. So that's the amount of cable that's still down there. As Stuart says, it's almost all abandoned in place, certainly the deep sea sections. So
wow. Okay, yes, there's a lot of stuff down there. Anthony's iPad says, I'm sure Anthony's iPad is meaning Anthony something else. On your maps, there are many cables looped around the coasts. Is it easier to lay cables under sea rather than across land?
Yes, especially in South America and Africa in the 1800s, where the inland was either inhospitable or impenetrable. And they tended to find that if they put a cable on poles, the poles disappeared. If they tried burying it, it was just dug up and it disappeared. So it's much easier to run it offshore. And even today, it's actually easier to run around the coast with a T in, a branch in to shore, because you can avoid inhabited areas and bad terrain and so on. So and tends to be in coastal countries, like that. Most of the habitation's around the coast anyway. It's like Australia and Africa in many places, and South America. A lot of the population density is around the coast, so it makes sense to run the cables around the coast and then just tap into them.
Yeah, there was a wonderful map you showed there, Bill, of I guess it must have been Cable and Wireless, and it was showed right down the bottom right-hand corner, Australia with a terrestrial cable going from Darwin down to the south coast.
Oh,
and
yeah.
Of course, there is now a project called either Inligo or Inligo, I'm not sure how you pronounce it, who are doing exactly the same. It's going up to Singapore and it's going across to Hawaii in the US, and probably Stuart knows exactly what I'm talking about. But it's probably got an NDA, so you can't talk about it. But it's funny that there's still the same routes being used today, 100 and something years ago later.
Yeah, you want the shortest distance between the population centers. That's where the business is, and the geography doesn't change. I'd say the main difference seen is the Pacific cables, because of the development of industry in that part of the world.
Yep. And you mentioned satellites, and in fact, there was a cable that was inaugurated 2020, I think it must have been, to a lot of islands across the Pacific, including the Cook Islands. And I talked to, just before it was turned on, the people who ran the Cook Islands operation, Ranulph Scarborough, who's a Brit, who used to work for BT. He's now back in Cornwall, but he did super fast Cornwall about 10, 15 years ago as well for BT. And that went via the O3B satellite, which is one of these low to medium Earth orbit satellites. And the latency was great. I mean, I couldn't tell that it was a satellite, not a cable. And the quality was wonderful. Yeah.
It's just that it's flying past at a tremendous rate.
Well, exactly.
Low Earth orbit, yeah.
Alan, can I interrupt again?
Yes, go on, Stuart.
Going back to this idea of it's easier to lay submarine cables. One of the things, obviously, we haven't covered millions of things in this talk, but one of the things that came with fibre optics is what's called repeaterless systems, which connect shorter distances, although nowadays, with limited capacity capability, they can stretch to around 600 kilometers of cable without having a repeater.
I didn't realize it was as much as that.
That cable that you showed your sample of, that cable you showed your sample of, URC2, is Alcatel's repeaterless cable design. It's not meant to carry power. And those were used for coastal festoons or inter-island connections where you don't need the higher capacity. So obviously they were brought in because it was cheaper to loop down a coast than to dig trenches and get all the permits and wayleaves to bury or put up on poles a fibre optic cable along the terrestrial area. So yes, it is cheaper, and it's an area of the market that has boomed like the rest of it.
Oh, time for a new article, Stuart.
And finally, it's now 9:05, so this has been great. Bill, you have to tell us what's lurking over your left shoulder.
Oh,
of
the
your-
equator mass and the equator mass and the pit scene.
Yes, it's some strange monster that looks as though it's about to leap over and get you.
Oh yeah, it's one of the Martians.
Right. Okay.
Yeah.
So this is a BBC background that you're using.
Oh yeah, it's a scene from Quatermass, of the set.
And there's a skull as well.
Oh yeah,
Good.
all sorts of neat stuff. Yeah.
Any further comments? I think we've had a lot of thanks from various people. So thank you. I will echo that. And Bill, this has been great. Thank you very much.
Thank you all for your attention. It's rather densely packed hour and a bit. It's a lot of information to try and get across, and so I hope I wasn't too much in places. But
no, that was great. Thank you very much.
Thank you all for watching.
Just a last quick one. Sorry.
Yeah.
Alison has put a question up there about the book I was talking about.
Oh,
And I
yes.
think she means the one about the Faraday, which is not a book yet. It's a draft that Bill and I have put together.
About the cable ship.
Yeah, it's about the Faraday's history, over 50 years of laying cables, which I think she was talking about her great-grandfather being involved in laying cables in South America in the 1850s, 1890s or whatever. And yes, we covered that in the book.
Okay, so Alison, stay tuned to our Facebook group, Greenwich Industrial History Group, and we will let you know when the book comes out and you can read more, and we can get Stuart and Bill back to talk about Siemens in Woolwich and what they did.
Oh yeah, we could do several hours on that too.
Mary, are you wanting to say something?
I was only going to say that the next book is on the 15th of March, which is Mike Neville, who is the National Industrial Heritage Support Worker. And he's going to tell us about what he does and how he came to be appointed and things like that. But what we've had of him in Greenwich, that before COVID, there was a big meeting at Crossness to set up a sort of liaison committee between all the London various industrial heritage groups and museums. But unfortunately, the follow-up meeting, which was to be at Three Mills, has never happened. But anyway, Mike will be able to tell us what's happened around the rest of the country and what he hopes to do in the future.
That's good. So that's 4 weeks today, in fact, Tuesday, the 15th of March.
Yeah.
Lovely. We shall look forward to that. Keep an eye on the group. Somebody's just put their hand up. David Hilton?
Yes, it was just one question that I hadn't had an opportunity to ask, which was just worldwide, with obviously the big geographical distances involved. I just wondered if the sources for the cables that are actually manufactured, are they all manufactured by one manufacturer, or are there several factories throughout the world? And the same thing for regarding who does the laying of the cables or pulling them up when they get damaged and need refixing. Is it all sourced out by one company, or are there various vendors throughout the world that cope with it?
I'm sure Stuart can answer that one.
Yes, I was thinking Stuart.
Okay.
It's your day job, Stuart.
Right, manufacturers. For repeated submarine systems, there is Subcom LLP in the USA. There is Alcatel Submarine Networks, which are now not part of Alcatel, even though they continue to hold the name.
Owned by Nokia.
They are owned by Nokia, yes. They have their repeater and terminal equipment manufactured in the UK at Greenwich, but their cable is manufactured in Calais. There is what we call Japanese Inc., which is Fujitsu and NEC, who make repeaters and terminal equipment, and their cable is made by OCC. There are smaller companies that make repeaterless cable, like Nexans in Norway, and there are some companies in China, but not many people deal with them for obvious reasons. And of course, Huawei Marine do offer submarine cable systems, repeated and unrepeated submarine systems, but again, there is the concern about Huawei and hidden spy software in the firmware on their equipment. So they haven't got a great market around the world. When it comes to maintenance or laying of cable ships, Subcom, Alcatel have their own fleet of cable ships. NEC and Fujitsu use KCS or Global Marine. Global Marine is an independent marine service provider, used to be part of Cable and Wireless. For marine maintenance, the world is divided into zones where the cable owners negotiate 3-year rolling contracts with marine service operators, and people who own cable ships, which I've really discussed the main suppliers of cable ships already, have ships on standby 24/7 to go out and repair the cables. So there are maps of where these ships are based, and they look after a large number of cables, which is funded by the owners of those cables. It's what we call self-insurance. You can't buy an insurance policy for a submarine cable.
So yeah, the cable ship that's Reliance, I think it's called, that's off the coast of Tonga at the moment as we speak, is a Subcom ship, and there's a cooperative of that sort of southwest Pacific.
Yes, she's part of a private maintenance agreement, and is her base port where a cable depot is in American Samoa, and that's the CS Responder.
I thought it was the other Samoa, the non-American Samoa, because that's where they put in.
It's an American ship in an American.
Yeah. Okay.
Which is not too surprising.
Yep. Okay.
They get certain tax breaks for being there.
Ah, right. Yes. Okay, but it was actually 3-4 weeks ago. It was off Papua New Guinea, where it started its voyage.
Yeah, there's a difference between its base port and where it is any time in the Straits every year, because it was actually maybe out on repair.
I think it was a cable laying project, wasn't it?
Well, that's the other thing. These maintenance agreements allow them to go and do outside work to reduce the annual cost to the cable owners. But of course, Murphy's Law says when they're loaded up with cable for a 3 or 4 week laying operation, that's when the cable goes down.
Absolutely. Yep. Okay. So, Bill, and thank you for all the questioners, and thanks to Stuart as well for answering some of the questions. Bill, thank you very much indeed for speaking to us tonight. Your afternoon. It's now 4:10 in New York, and it's 9:10 here in London. So thank you very much indeed, Bill.
Yeah, glad I was able to fill in for Cassie at rather short notice. And
yes, well, thank you, and best wishes to Cassie for.
Yes, indeed.
And we will try and get her back as soon as we can, as soon as she's better, and as soon as we've got another slot. So thank you very much.
Thank you, Alan.
Thank you all. And I say the recording, keep an eye on the website. On the Facebook group, we will let you know when it's up and available to watch on our YouTube channel. Thank you very much. Goodbye, everybody. Thank you, Bill. Thank you.
Thanks, Bill.